Today I discuss the order topology. In beginning, I start the definition of order topology. But I first discussed previous class, and in previous class we talk about basis for a topology. Basis is an important role in topology. We start about definition. Each and every element of these sets, basis element containing this element, and obviously one element contain two different element of basis, then one third element of this basis obviously contain this element of the set. In this way we define the basis, and then we some basis generated topology we define, and we create some examples, some circular region, some rectangular region, and some others example. That means collection of all one point sets and from discrete topology. Then we also done the some lemma. Lemma tells us that the topology equal to union of elements of basis element. And also next lemma tells us that topology contain some collection of elements, and these collections of elements also contain in some open set U of X, and then this collection of elements is from a basis for topology. And next we discuss comparable with two topologies, tau and tau dash. Tau dash is finer than tau, then obviously script beta dash, one element find in script beta which is the basis for tau, and script beta dash is the basis for tau dash, then obviously this element contain some beta dash. This beta dash must be contained in beta. And also we give some familiar example of this. That means some circular region and some rectangular region, they are both comparable with each other, then we call them they generate same topology. And next we discuss standard topology, some collection of open sets in R. And next also discuss lower limit topology, closed A open B, where A less than equal to X less than B is the basis element for lower limit topology. And also we discuss K topology. K topology is the this collection, that means basis element, those collections of elements of all open intervals AB along with the sets of the from AB minus K, where K is 1 by n where n belongs to Z plus, those sets. And this beta double dash from a topology, this topology is called K topology. Then we also further discuss lower limit topology RL and K topology RK, also strictly finite than the standard topology and are not comparable with one another. Also we define some basis and then subbasis. Subbasis which one? Subbasis is a collection of subset of X which union equal X, and obviously some basis element is the finite intersection of some subbasis element. That means some basis element is the finite intersection of some subbasis element, and topology is the union of basis element, that means union of some finite intersection of subbasis element. Next we define some topologies by some example given. which one is the smallest and which one is the largest, and we all are see in previous class. So now we start the order topology. Order topology, at first I start some familiar intervals, those we are known. Which interval? Open AV. Open AV is equal to, we define x such that a less than x less than b, and open A closed B. This interval define x such that a less than x less than equal to b. Also closed A open B define x such that a less than equal to x less than b, and closed A B define x such that a less than equal to x less than equal to b. Those intervals are all known previously, so we just read it and all are also understand of those intervals. Now discuss some definition of order topology. Let X be a set. Here X be a set with a simple order relation. Which one is simple order relation? Simple order relation means comparability. That means X not equal to Y, otherwise X related to Y or Y related to X hold, and no reflexivity exists. That means X is not related to X, and also transitivity exists. That means X related to Y and Y related to Z. That means this implies that X related to Z. So here X be said with a simple order relation, and SM X has more than one element. That means cardinality of X obviously greater than 1. Okay. Let script beta with a collection of all sets of the following types. First one, all open intervals AV in X. Second one, all intervals of the form closed A0 B open. A0 is the smallest element of X. 3. All intervals of the form open A closed B0, where B0 is the largest element, if any, of X. Then the collection script beta is basis for topology on X, which is called the order topology. So we understand the order topology. Just we first define some collection of sets. Those collection of sets coming from a set X, and this set's cardinality must be greater than 1, and then this collection of sets of following types. That means this collection contains some open intervals AB, and which one is belongs to X, and also some closed open, that means half open interval or half closed interval, close A0 comma B open. In this way, some where A0 is the smallest element of X, and also open A and closed B0. That means B0 is the largest element, if any, of X. Then in this collection, in these three types of intervals are belong to this collection, and this collections from a topology. This topology is called the order topology. Now it defines some example, some familiar example. We first see it. Which example is most important for us? We first start standard topology. We all know that open interval AV, where L less than V, is the basis element for standard topology on R. Then we first start standard topology. Standard topology. We all know that open interval AB, where A less than X less than B are the basis element for the standard topology, and it denoted by R. Then the order, also this one is the order topology. Also this one is the order topology derived from the usual order. That means we considered usual order. We considered usual order. Then this standard topology become a order topology. I think we are all understand about this familiar example, some standard topology and also some usual order, then R becomes order topology. Next, we discuss another familiar example, which one also known for us. Construct R Cartesian product R, and also consider dictionary order. Dictionary order. That means all elements x cross y are the elements where x belongs to R, y belongs to R, and R cross R has neither largest element nor smallest one. Then R cross R has a basis, the collection of all open intervals. R cross R has a basis, the collection of all open intervals of the form A cross B, C cross D, where we define for A less than C, or if A equal to C, then B less than D. In this way, we construct a basis, and this basis form an order topology on R cross R. The collection consisting only intervals of second type. That means we construct two types of interval. If A less than C, then this figure is here. In this way, A cross B, here C cross D. Then which one? A less than C, this way, and here just here A cross B and A cross D. A equal to C here. That means in second type, this type form an order topology for R cross R. For R cross R, this relation from an order topology. So we understand this example, very simple, just Cartesian product of R cross R, and we define dictionary order. Element are those type x cross y, x belongs to R, y belongs to R. R cross R has neither largest element nor smallest one, and R cross R has a basis, the collection of all open intervals of the from. In this way, for A less than C, one type, another type equal to C, and B less than D, then this type, and this type from order topology. In this type form, the sub collection consisting only intervals of this type for is also a basis for the order topology of R cross R. This type is the basis for the order topology of R cross R. Next, we discuss also a familiar example, also known to all. Z plus from an order set with the smallest element. Z plus also from an order set with smallest element. If n greater than 1, then n equal to n minus 1, n plus 1 open interval. That means these are the basis element for Z plus. If n equal to 1, then also 1 equal to 1 2 is the basis element. So Z plus from an order set with smallest element 1. Also we construct some 1-point set. Then these 1-point sets are the basis element of for Z plus, and this basis element from an order topology, and this one is the discrete topology. The order topology on Z plus is the discrete topology. Okay, now next one is one of the important example and harder than previous ones. Which example? We take one set x equal to just 2-point set 1 2 Cartesian product Z plus. Then elements are those 1 1 1 2 dot 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 1 8 dot 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 2 1 2 2 2 n in this way. These are the set X, and we define also here dictionary order. In this way, we denoted this element A1, this element A2, this element AN, this element V1, this element V2, this element Vn. Then in dictionary order, we know that if this one is 1 equal to 1, then 1 less than 2. That means this one in some order, maintain some order. And here also 1 less than 2. That means this one is first category. Okay, this one is second category. Here all 1-point set. Here all 1-point set except this B1. Except B1 from basis of the topology. That means all 1-point set, any open set containing this B1 also contains some A1. How? Any open set we take from here. Here all sets are open. If we take from just B1, then B1 contained in, that means in dictionary order, any open set containing B1 must contain a basis element about B1, and any basis element containing B1 contains point of A1 sequence. How this one is possible? That means B1 equal to 2 1. This point of this set. Now we define the topology. That means all an order set with the smallest element the order topology is here define some order topology, and this topology most one point sets are open, but is one exception, the one point set B1. This one is not discrete. B1 means if we consider a key 1 key, that means a key if 1 less than 2, then a k obviously less in dictionary order B1. So in any open set containing this B1 must contain some element of AK. Okay. So in this way we find any basis element containing this B1 must contain some AK. AK this order is the some dictionary order. Okay. In this way we find any open set we construct from X, and this contain B1 obviously contains some element AK. So this from also a order topology, but this one is not discrete topology. Now discuss some range or definition of range: open range, closed range. Definition: we know that if X is an order set, if X be an order set, and A belongs to X, then there are 4 subsets are called range determined by A. There are 4 subsets which called range determined by A. They are open A plus infinity. This define X greater than A. Here minus infinity A, X such that X less than A. Closed A plus infinity. Here X such that X greater than equal to A. Minus infinity closed A. X such that X less than equal to A. In this way we define 4 ranges, and first 2 are open range, next are closed range. So we construct if X has a largest element B0, then if X has a largest element b0, then a infinity equal to or approximate to a b0. And in this way we define some or approximate to a b0 if a plus infinity defined as in this way, then also minus infinity we also define if a0 is the smallest, then a0 b. So here we also discussed order topology. That means order topology defined in some, that means order is here exists if ordinary order or dictionary order, any type of order exists, and this order from some basis element, and this basis element creates some topology. So here we today discuss order topology, and we are all understand, I think. So thank you.